Welcome to Review Lecture number 16 for our online review course of Undergraduate Probability and Statistics. I'm Chris Mack, your professor for this class, and Lecture 16 is the second to the last lecture, the penultimate lecture in our series, and is the first part of our two-part series on linear regression. Before we begin discussing how to regress data with a model, that is, how to find the best fit parameters of some linear model, we must first define that model. So let's take a look. We'll use the ideas of random variables. We have a x random variable and a y random variable, and we'll ask the question, what does it mean if we say that these two random variables are linearly related? Well, the first approach you'd probably take is simply say, well, if they're linearly related, then y must equal a times x plus b, where a and b are scalars. If you think pretty closely about this, however, you'll see that once we have a value for x, it determines the value for y exactly. Well, this would make sense if, for example, x were the random variable temperature in degrees centigrade, or degrees Celsius, and y is temperature in degrees Fahrenheit. Well then, yes, this would be a perfect model for converting a random variable degrees Celsius to a random variable degrees Fahrenheit. But is that really what we want to do? Normally, we have variables something like reaction rate versus temperature, or yield versus the thickness of a layer in my process, or some other sets of parameters that I want to create a linear model for. In that case, we have variation in y that is explained by the variation in x in a linear way, but we probably also have some variation in y that is independent of the variation in x. For that, we need a more sophisticated model when we think about this model in terms of two random variables, y and x. And this will be our second approach, the preferred approach, the only approach that really works for our problems. And that is, instead of saying y is equal to ax plus b, we'll say that the expectation of y given a certain value of x is equal to ax plus b. Now, what does that mean? This means that the mean of y is controlled by the random variable x, and that there's extra variation in y that comes about independent of the variation in x. The perfect simplest example of this is measurement error. I'm measuring x, I'm measuring y. X affects y in some linear fashion, but there's uncertainty in the true value of y because I measured it. And every measurement has uncertainty built into it. Well, the uncertainty in the measurement has nothing to do with how x influences y. It's an added uncertainty that comes from a different mechanism than the linear model that we're bringing about. So we're going to say that the conditional expectation, the expectation of y given that we know what x is, or that x takes on a certain value, is a new random variable that will be linear related to x. Now, what is a conditional expectation? It's technically, mathematically, it's defined in terms of conditional PDFs or conditional PMFs, probability mass functions or probability density functions. And I've chosen not to go through that discussion in this review lecture. If you're interested, some of the textbooks that I've recommended, or many other textbooks on the topic of probability and statistics, will include a discussion of conditional PDFs. I'm just going to skip it. So some of this you'll just have to trust me that this is how it works, but I'd rather you understood intuitively what this means. This means it's the mean of some distribution of y that's controlled by the random variable x, and not all of the variation in y is controlled by the random variable x. The one property that we're about to use is called the law of iterated expectations. If I take the expectation of the mean value of y given x, I simply get the expectation of y. We'll use that on the next slide, as a matter of fact. Okay, so what does our model then tell us? We've got a model, and suppose we took the expectation of both sides of this equation. The law of iterated expectations would say the expectation of this thing is simply the expectation of y. I take the expectation of the right-hand side, I get a times the expectation of x plus b. Well, with that, I can solve for b. And I find that b is equal to the expectation of y minus a times the expectation of x. If I have a set of data, I can figure out an estimate for the expectation of y, simply the mean of the data in y. I can figure out an estimate for the expectation of x. It's simply the mean of my x data. So this says b is going to be the mean of the y data minus my slope times the mean of the x data. So now if I had an estimator for the slope, I would be able to calculate the intercept b. Well, this brings up the next set of the derivation, which I will again skip and simply show you the results. And it involves the covariance of x and y. Now, you might expect that that is the key thing we're looking for. If x and y have any kind of linear relationship with each other, then something about the covariance of x and y, how x and y vary together, must tell us something about this linear relationship. So I write down the definition of the covariance of x and y. It's the expectation of x minus its expectation times y minus its expectation. And I carry out that calculation, and I find, assuming this linear model, that the covariance of x and y is simply a times the variance of x. So whatever variance I have in x, I multiply it by this slope a, and that tells me about the covariance of x and y. It's sort of, if you think about it, it does make intuitive sense. But what this allows me to do is solve for a, the slope of my linear model. A is simply the covariance of x and y divided by the variance of x. All right. Now, let's put that all together. We have a linear model which says the expectation of y given a certain value of x is equal to ax plus b. Or the mean of some distribution of y at a particular x value will equal ax plus b. How do I find the a and b parameters? B is simply the expectation of y minus the slope times the expectation of x. And our slope is the covariance of x and y divided by the variance of x. We are done as soon as we have estimators for these four statistics. E of x, E of y, covariance of x and y, and the variance of x. Now, guess what? We've already discussed all of these things. We've come up with estimators for each one of these. But that brings up an interesting point. We came up with some estimators, which are good ones, but they're not the only estimators. There are, in fact, multiple estimators for each one of these quantities. So let's go back to the topic of an estimator and ask our question, which estimators are the best for each of these quantities? And how do we define what we mean by the best? Well, we've talked about this a little bit already, so let's review that. If I have some parameter theta, maybe it's the mean, maybe it's the variance, maybe it's the covariance, it could be any parameter that we might want to think about. Then we have some estimator, theta hat, for that parameter. Our goals in having a good estimator is that we want this estimator to be unbiased. What that means is the expectation of theta hat equals theta. In other words, if I let my sample size get larger and larger and larger and larger, our estimator should converge to the correct value. That means it's unbiased. We also want our estimators to have a minimum variance. That is, the variance of this estimator should be as small as possible. Now, it will never be zero in any real situations, but we can certainly have estimators to compare the variance and find one to be smaller than the other. And finally, we would like robustness from our estimators. Robustness means if I have some bad data points, there's, for some reason, some data point got screwed up and is 100 times too big. I would like to have an estimator that would not be completely ruined because of this one bad data point, or two bad data points, or maybe a lot of bad data points. So if I have some reasonable fraction of the data that turns out to be bad, will my estimator still give me a reasonable result? That's robustness. There are many different estimators for each parameter, and these estimators tend to have trade-offs in terms of bias, variance, and robustness. The ones we've talked about a little bit are estimators for the mean. We can use the sample mean, we can use the sample median, and we can use the trimmed sample mean as estimators for the expectation of x. Which of these are better? Well, the mean is unbiased and has the minimum variance. The sample mean is unbiased and has the minimum variance. That's why we usually use it. The median, however, is biased if I have an asymmetric distribution, but is unbiased if I have a symmetric distribution. And it is robust. I can have a lot of bad data points and it doesn't affect my median very much. But it has a larger variance than the mean. A good compromise is the trimmed mean, where I throw away the highest 10% of the data and the lowest 10% of the data, for example. That means I can have 20% of my data points being bad data and I still get a good value. It has a slightly bigger variance, but it is robust at up to 20% of the data, and it's unbiased even if I have an asymmetric underlying distribution. So you see there are trade-offs for these properties, and one estimator that does it all generally doesn't exist. Now, with that discussion in mind, let's talk about the most important kind of estimators and the most popular kind of estimators used in all of statistics, the maximum likelihood estimators. Suppose I run an experiment and I get a set of data, x1, x2, etc. up to xn. So our sample size is n. What the maximum likelihood estimator does is it asks a simple question. What value of the parameter we're interested in will maximize the likelihood of getting this exact data set? Obviously, any particular data set that we might get is unlikely. If I ran this experiment again, I'm going to get all different sets of data. But given that I did get this set of data, what value of the parameter, the unknown parameter that I'm trying to estimate, what value of that parameter maximizes the likelihood of getting this exact set of data that I actually got? What I would have to do to answer this question is define the probabilities. So what probabilities are we interested in? The probability that the random variable x1, that is the outcome of the first measurement, equals the actual value I got, little x1, given that the value of the parameter is theta. And then I say, what's the probability that the second measurement, random variable x2, turned into its exact value, little x2, given a certain parameter value theta? And I do that for all of the parameters. Excuse me, all of the data points, x1 through xn. Now, I will assume that each measurement is independent. So, if each measurement is independent, then the probability of getting that entire set of data is simply the products of the probabilities of getting any individual data point. So, we will define the likelihood function as the product of all of the individual probabilities. So I'll take this probability for x1, multiply it by this probability for x2, etc., all the way up. Then I will evaluate the likelihood function, and maximize it. Of course, we'll maximize things by taking derivatives and setting them equal to 0. But in order to do that, what do I need to know? I need to know these probabilities. In other words, I have to have a probability model, which means I have to make an assumption about the underlying distribution of each of the data points, x1, x2, etc. So let's take an example. Let's suppose that each measurement, x sub I, is normally distributed, has some mean and some variance. We'll then suppose that every one of the individual data points are identical and independent. So they're independent and identically distributed, IID. Notice we've made a lot of assumptions here. It may not be true that every data point is identically distributed. Sometimes when we make measurements, let's say we're measuring temperature, maybe our temperature measurement is more precise at the high temperatures and less precise at the low temperatures, or maybe the opposite. We might not have the same variance in our measurements for all values on the temperature scale. Right? But sometimes we do. So we have to check these assumptions. Also, it's very common to have measurements that are not normally distributed, but sometimes they are. So let's make this assumption, and then later we'll have to check it with our data. Now, let's find the maximum likelihood estimator for the mean, mu, for the set of data. Well, the probability that any given measurement turned into the exact number that I got, given a certain value of mu, actually it's given a certain value of the variance as well, will be equal to, well, that's simply the equation for the normal distribution. I plug in the number for xi, and this says the probability of getting that particular value of xi. So what's my likelihood function? My likelihood function is the product of all of the probabilities for all of the different xi. So I take product as I goes from 1 to n, that is my whole sample, each of these probabilities, and then I multiply them all out. When I do that, the term in front gets to the power of n, and then because I'm multiplying a bunch of exponentials, the result is the sum from I equals 1 to n of all of these terms, xi minus mu quantity squared. Okay, I've got a likelihood function. What do I do with it? I want to find the value of mu that maximizes this likelihood function. In other words, I'll take the derivative of this equation with respect to mu, set it equal to 0, and then solve for the value of mu that satisfies that equation. Now, as a hint, because of the exponential nature of these equations, if I take the logarithm first, then I take the derivative, it makes the math a lot simpler. The log of a function will reach its maximum at the same place as the function itself. So this is typically how we actually work it out. But you could do it the hard way if you wanted to as well. Take the derivative with respect to mu, set it equal to 0, then solve for mu. The result you will find, if you are interested in going through that math, and I do recommend the exercise, the result is the familiar formula for the sample mean. We'll get a sample mean expression back for our maximum likelihood estimator for mu. Okay, so here are some maximum likelihood estimators for all of the parameters that we're going to need for our linear regression, assuming IID normal distributions. Okay. Our estimator for mu, it's now called mu hat, is this standard sample mean. The estimator for the variance is 1 over n times the sum of xi minus x bar quantity squared. Or I could have written mu hat here. Same thing, right? Our estimator for the mean. Covariance, also a familiar formula. Notice that these MLE estimators have 1 over n in the equations, And we've been used to using estimators with 1 over n minus 1 in them. So our estimator for the sample variance, we typically pick 1 over n minus 1. Why is that? Well, the maximum likelihood estimators for variance and covariance are biased. If I took the expectation of these values, I would not get the true mean. The mean's unbiased, but the other two estimators are biased. If I took the expectation value of this estimator, I would not get the true variance. I would get a slightly different value, which I can correct if I replace n by n minus 1 in both of these equations for the variance and the covariance estimators. And we typically do that. The result, though, is an estimator that has a slightly bigger variance, and it is not exactly equal to the maximum likelihood estimator. Unless n is really, really small, though, the difference is pretty slight, and we can generally ignore it. I would also mention that these estimators are not robust. Even one bad data point will completely screw up all three of these estimators. So, if we want to use estimators that are not robust, we must be very careful looking for bad data points. So there are limitations to the maximum likelihood estimator. Nonetheless, it's still a very valuable, very popular estimator to use, and it's the one we'll use for our linear regressions. So we're back to our model, the linear model here, and how we calculate A and B from that linear model, and we use the maximum likelihood estimators. We use our maximum likelihood estimator for the covariance, divide by the maximum likelihood estimator for the variance, and we get this formula for the slope, this formula for the intercept. And if you've seen linear regressions before, these are the formulas you've seen. Interesting note. The n, 1 over n up here and the 1 over n down here cancel out, which means if I had used 1 over n minus 1, that is the unbiased estimators, instead of the MLE estimators, I would get the same result for A. So, our maximum likelihood estimator for the slope and the intercept are also unbiased estimators for these two parameters. And that's only because the 1 over n or 1 over n minus 1 will cancel out here. Well, that's the maximum likelihood estimators for the parameters A and B of our linear regression. But you might be thinking, wait, I've learned something different. I've learned about least squares regression. What does that mean? How does that relate? Let's take a look. A least square error regression goes something like this. We minimize the square of the difference between the model and the data. So we'll write our model in a slightly different way. In fact, it's actually an equivalent way of writing our model as before. But we'll say that every measured data point yi is equal to a times a measured data point xi plus b plus an error term e sub I. And that error term is called the residual of our model. Now, if I took the expectation of all of this, I would find the expectation of y, the mean value of y, is a times the expectation of x plus b plus, well, the expectation of the residuals will be 0 for our best fit. And we'll end up with the same kind of results we were getting before in our model based on random variables. So in fact, this is an equivalent version of the model. The model assumes all uncertainty comes from y. There's no uncertainty in x. It's like saying y given x. X is a given. Now what happens to y? Well, there's a mean value, which is controlled entirely by the x, and then there's some residual, and some uncertainty in y that is independent of the x value. Now, we find the values of a and b that minimize the sum of the squares of the residuals. So the residuals are also called the errors. So the sum of the squares of the residuals, we'll give the letters SSE, sum of squares of errors. So I take the residuals, I square them, and then I add them up from 1 to n for my entire data set. And that's equivalent here. Now, what values of a and b minimize the sum of squares? Well, that gives us the least square error. So I take this equation, I take the derivative with respect to a, and set it equal to 0. I do the same thing. I take the derivative with respect to b and set that equal to 0. I solve for a, I solve for b in those two equations. The result is our least square estimate for a and b. Some properties of this least square error solution. As I said, the residuals have a mean value of 0. Also, if we want to estimate the variance of E, our unbiased estimator for the variance of epsilon, I should say, the residuals, is the sum of square errors divided by n minus 2. I divide by n minus 2 because I have two parameters, a and b, in my linear model that affects the degrees of freedom in the residuals epsilon sub I. When I look at the solutions, I will find the equations that tell me what the slope is and the equation that tells me what the intercept is, given my set of data, is exactly the same as the MLE estimates. In other words, least squares errors produce the maximum likelihood estimator. But only for the case when we assumed our data is IID normally distributed. And remember, that was the first assumption we had to make before deriving the maximum likelihood estimator. If we assumed something else about our data, that it had some distribution other than normal, or that there was some variation, some systematic change in the parameters of the distribution, such as the variance, then this would not be a maximum likelihood estimator. So, our motivation for thinking about regression and the least squares error approach is simply that the least squares error fitting produces the maximum likelihood estimates of A and B under the assumption of IID normally distributed data. All right, let's review our penultimate lecture, number 16. What have we learned? As always, you should be able to quickly and easily answer these questions. If not, you need to go back and review the material again. What is our model for a linear regression? What four statistical parameters must we estimate in order to find the slope and the intercept of our line? What is a maximum likelihood estimator? What is a least squares estimator? And finally, when do MLE and LSE give us the same answers? Well, that's the end of our first part on linear regression. We're going to end the review course on undergraduate probability and statistics with lecture number 17, the second part of our two-part series on linear regression. Till then.